All right. So we were trying to see a proof of a decomposition theorem. So V is a space of functions from Z mod Pz to R. So this is a finite dimensional vector space. And we had a set K1 to be equal to those functions f belong to V such that 0 less than equal to f less than equal to less than equal to 2. Okay. And K2 to be equal to the set f2 belongs to V such that norm f2 is less than equal to some parameters of some small. Okay. Here also I will replace this 2 by 1 minus delta inverse. Okay, delta will be some small parameter. So we want to write down a function f as a sum of functions from K1 and K2. So we want to write for f belongs to V such that f is equal to f1 plus f2 with f1 belongs to K1 and f2 belongs to K2.
Which norm is that?
So this norm, so this I am right now, this norm in our application will be a cut norm defined by Conlon, Fox and Zhao, or it may be a Gauss norm defined by this thing. So at the moment first I will obtain a sufficient conditions, we'll write down the sufficient conditions which will work when the norm is the one which is defined by the Conlon, Fox and Zhao, but will not work when the norm is defined by the Gauss norm. Okay? But it is some norm. At this moment, we are not worrying about that what is the norm for it, what exactly is a norm. We are just working in an abstract setting. In our application, it will be a norm which controls the k-term arithmetic progression. So f is equal to f1 plus f2 means that because we are our eta will be small in our applications, means that gamma kf is nearly equal to gamma kf. Because the other thing, the Gauss norm or the Conlon-Fox-Zhao cut norm is small, so therefore that will not affect the k-term arithmetic progression, the count on the k-term arithmetic progression. That will behave like an error. Okay. Okay. But in either case, what we notice is, first thing is that K1 and K2 are convex sets. All right. Both K1 and K2 are convex sets. So their sum is also a convex set. and hence K1 plus K2 is convex. Sum of two convex set is convex. Okay? So, okay, before I give you a sufficient conditions for this, so let me just do a very quick properties on the finite dimensional thing, so which will be important for us. Okay, so just to quickly review the things which we require. So, since V is a finite dimensional vector space, if are two norms, then there exists C1P, C2P greater than 0 such that all right. In other words, all the norms are equivalent. So therefore, the topology defined by any two norms are equivalent. So, all right. So therefore, when I say closed set, I don't have to specify which, with respect to which norm I am talking about. When I say compact set, I don't have to specify with respect to which topology I am talking about. All right. So now this K1 is a closed set with respect to the L infinity topology. And in fact, it is a compact set. K2 is a compact set with respect to this particular norm, whatever it may be. So therefore, K1 plus K2 is compact. Sum of two compact set is compact and hence closed because topology is Hausdorff. All right. So now we will consider the V star to be the function H from V to R, the dual space. H is linear. Okay. Again, because all the topologies are equivalent, all the linear maps are continuous. And given H belongs to V star, we can write H of F. There exists phi belongs to V such that H of F is equal to phi of X, which I will denote by F phi. Okay. So this, just remember that, we use this notation generally for the inner product in the L2 space, but here is just all the topologies are equivalent. So now dual norm. So given a norm on V, we define dual norm, which is defined as norm of f star by definition is equal to supremum of f all right. In fact, what we have is we don't need to take modulus, we can just take work without modulus. So primum over in a f and g, because just for the fact that if f and g is less than 0, then f and minus g will be equal to modulus of f and g, and norm of minus g is same as norm of g. So using this, we get actually the dual norm is same as a supremum of inner product f and phi with fg norm g less than equal to. All right. Then what is the meaning of algebra norm? So V is not just a vector space, but it is also a algebra under pointwise multiplication. If you have two functions, you can multiply them. And if you are looking at Rn, then just a coordinate-wise multiplication, x1, x2, x3 into x, y1, y2, y3 is just x1 into y1, x2 into y2, and x3 into y3. Is said to be an algebra norm if two things happen. Norm of the product is less than equal to the product of the norms. Norms, first condition, and norm of one is equal to norm of is equal to 1. All right. Okay, maybe it is a good idea for me to prove the result, which I will need to deduce from the algebra norm. What is why I will need an algebra norm? So just very forward. be a norm such that its dual is an algebra norm Yeah, okay. I should have probably thought of, but I am not thought of this, giving an example where dual of an algebra norm need not be an algebra norm. So, yeah, good to have an example of a norm such that, so that I cannot, if the dual of an algebra norm would have been an algebra norm, then I need not write let be a norm such that its dual is an algebra norm, because I can just write that this is an algebra norm. But dual, one should be able to construct an example such that the dual of an algebra norm need not be an algebra norm. Then you have two things, that L infinity norm of a function is bounded by this dual. Okay. So let me prove the second part first. For this, I need the following thing. So, okay, let me write down the claim. Second part of the claim. It is sufficient to show that if then norm then its L infinity norm is also at the most 1. Okay. So for this, one can just see that this has got nothing special about the two things. If norm 1 and norm 2 are two norms, and then indeed this is just a simple exercise. So therefore, all right. So okay, so let me Okay, so okay, let me prove this thing. So, so if norm f star is less than equal to 1, then this implies norm of n star is less than equal to 1. F to the power m, let's say for all m belongs to the natural numbers, norm f is f to the power m star is less than equal to 1 for every integer m.
Star is an algebra.
Star is an algebra norm. Right? Now, now suppose norm of infinity is greater than 1. That means what? That there exists x belongs to z mod pz such that mod of fx is greater than 1. Okay? Now look at the indicator function of this x belongs to z mod pz. Indicator function of this particular x. Okay? Then what will be the inner product? And I can assume without loss of generality by replacing f by minus if I wish that this is actually the case. Okay? So that I don't have to worry about the modulus. If I have to replace f by minus f, then anyway both sides will not change. Doesn't matter. This will be equal to mod f to the power n x by p. All right? And hence will tends to infinity as n tends to infinity. This is just a, I mean, what it is the thing, just the definition from here to here. So it will be f to the n x by p. P is fixed for us, so as n tends to infinity, this is tending to infinity. On the other hand, by definition of the dual norm, this is less than equal to norm fn star into norm of this indicator function x. Now, x is fixed for us, it is not varying with the n, so whatever it may be, this is some fixed quantity. And this is less than equal to 1. So therefore, therefore we obtain a contradiction because this is bounded on one hand by some fixed number, which is independent of n. On the other hand, this is tending to infinity as n tends to infinity. So therefore, L infinity norm is bounded by this norm. In other words, okay.
Just take them through.
Nth roots.
Take and let everybody.
Oh yeah, means you are saying that this is equal to this thing, so mod fn x by p, and the right hand side is less than, yeah, 1 by n, so this is a fixed quantity, so okay, this will go to 1. Fine.
Balu will be happy because it's multiple integration.
Okay, whatever. Okay, so fine. So this proves the second part. Okay, I'll leave the first part. How much time do I have? 30 minutes. Okay, the first part I will leave it as an for you to verify. Okay, and it is this lemma which is where I will be using the condition that my norm is an algebra norm. I mean, that's why this decomposition will be easier to obtain for the Conlon-Fox-Rao thing, cut norms, and will be, because this lemma is not available for me when the norm, for the Gauss norm thing, because the dual there is not an algebra norm, and that's why the obtaining a decomposition for the Gauss norm will be slightly more complicated. All right, so now we have seen that this K1 plus K2 is a compact and hence closed convex set. So let me write down a Hahn-Banach theorem in a form which in a form which we need. Okay. I shall not give a proof of it, though the proof is rather simple, but I will not do it, just to save the time. Let K be a closed convex set of Rn. I need only for finite dimensional, okay? Because our space are finite dimensionals. And f is a function which is in Rn, which is not which is not in K. For ours, it will be V, the same thing. Okay? Then there exists phi belongs to Rn such that is greater than or equal to 1. And for all G belongs to K. All right. So you can obtain a function phi so that this f into phi is bigger than 1, and you can separate them by a linear functional or a hyperplane. So let us see what do if we apply for, okay. So now this, okay. Let me write down the statement first. This is what which we will need. So now we want to write down this. Actually, we want to obtain a sufficient conditions for this f, so that it does, cannot, if it cannot be written as f1 plus f2, then so if so corollary. If f does not belong to k1 plus k2, which is a closed convex set, then there exists phi such that greater than or equal to 1, and in a product f to g is less than or equal to 1 for all g belongs to k1, and norm of phi star is less than or equal to eta inverse. Let me write down, so okay. First this, and in a product f2 with phi is less than or equal to 1 for all f2 belongs to k2. Now this condition, f2 is a ball of radius eta with respect to this particular norm, okay? Therefore, this condition is nothing but saying that norm of phi star is less than or equal to eta inverse. I can scale it by eta, then f2 by eta, then it will be a unit ball. So therefore, and what is the norm of phi star is equal to supremum of f2 phi with all f2 in the unit ball. So eta times f2, if the f2 is in the unit ball, then the eta times f2 will be in my k2. Sorry? Here? Oh, sorry. Sorry. G. G. Okay? Is this okay now? Okay. So norm of phi star is less than or equal to eta. So now let me write down the statement. Moreover, let me say that, okay, I was saying that of course you cannot hope to obtain a decomposition theorem for arbitrary function, and which is also clear from the fact that k1 plus k2 is a compact set. Your entire space is not a compact set. So of course, every function cannot be written as a functions from K1 and K2. K1 plus K2 is not an entire space, because it is a compact set. Entire Rn is not compact. Given eta delta greater than 0, so I will write down now the sufficient conditions which I will say that we will write so that the function can be decomposed as can be written belongs to K1 plus K2. Okay. So if those conditions are satisfied and still though the function is not in K1 plus K2, then this corollary along with that particular lemma will give us a contradiction. So this epsilon depends only upon eta, will only depend upon eta and delta. It will not depend upon the prime p, and that will be very crucial for us. And no other parameter, basically. It depends on this particular eta and delta. That's it. It does not depend upon the norms which we are defining. It will not depend upon anything else. This V is a space of functions from Z mod Pz to R such that okay. So we are defining, we have a norm on V such that its dual is an algebra norm. Then okay, let f belongs to Z mod Pz to R plus be a non-negative function such that there exists V from Z mod Pz to R plus with the following properties. One, it dominates F. Two, its L1 norm is at the most 1. Three, norm of V minus 1 is less than equal to epsilon. Okay. So suppose there exists a function for which there exists another function v such that norm of v1 is such that it dominates f. The L1 norm of v is bounded by 1 and norm of v minus 1 is pretty small, smaller than this epsilon. Then f belongs to k1 plus k2. Okay. So such a v will be called a pseudo-random measure. So basically, if the function is dominated by a pseudo-random measure, then it can be decomposed into the functions we want. But a pseudo-random measure will have more properties than the ones I have written. But for the decomposition, I need only these two properties, provided that the norm which I am working whose dual is algebra.
V I consider.
Sorry?
The V I was writing.
Yeah. So okay. So okay. Yeah. Means this indicator function, this. Yeah, I mean, so for the three term, things are slightly simpler because, as I say, that you can convolve with the Bohr set, and the norm is basically a Fourier transform. And the Fourier transform behaves well with the convolution. So in this, so in the case of three-term arithmetic progression, you can explicitly decompose it as f1 plus f2. In this case, we are not giving the explicit decomposition. We are saying that there exists a decomposition. Eta and delta are there in the definitions of K1 and K2. If you want to control the norm of the error term by eta, then it must have if you want it to be good.
We go on 1 minus delta inverse.
And this is f2 such that the norm of f2 is less than equal to eta. For the better control, you should have a better property. Delta in our applications we can take to be a bounded thing, but eta we will want it to be small and small. All right, so let me now give a proof of this thing, this particular result. Suppose f does not belong to k1 plus k2. Then using this corollary, then there exists phi such that f phi is greater than 1 I am rewriting the corollary and doing nothing else. And F1 phi is less than equal to 1 for all F2 less than equal to eta. Okay? Now let me make give you a proof. Sorry?
Third line greater than 1?
No, less than equal to 1.
No, third line.
Yes.
Above.
Yes.
Above. This one.
Yeah, greater than 1.
Greater than 1.
Yes. Thanks. Yeah, this. Yeah, thanks. So now let me make a simplifying assumption that this phi which I have obtained is actually positive function. In general, this phi need not be positive function, and that's where I will need most of the conditions. But suppose I assume that this phi which I have obtained is a non-negative function. Then the proof becomes easier. And I will, okay? Proof of theorem, case, suppose phi is non-negative. Okay? That's a big assumption which will not be satisfied thing, and then what happens? F with phi, F is non-negative, phi is non-negative, okay? And F is dominated by V, so I can write down V phi. Because F is dominated by V, nu, therefore F phi is less than or equal to, so this inequality is true. If phi is if phi takes the positive as well as negative values, I cannot write down this. Okay? But this is equal to 1 phi plus V minus 1 phi. Okay? Now, 1 phi is less than or equal to 1 minus delta. Why? Because if I multiply by 1 to 1 minus delta inverse, the function which takes identically value 1, why? Because if I take this function 1, if I take function f is equal to 1 minus delta inverse, F1 is equal to 1 minus delta inverse, then this is still in K1. Okay? And then F1 phi will be exactly equal to but I wanted to write in this 1 minus delta inverse 1 phi. On the other hand, this should be less than equal to 1. So therefore, that proves that 1 in phi is less than equal to 1 minus delta. All right? Now, v minus 1 into this particular thing, this is less than equal to norm of v star into norm of v minus 1 by definition of a dual norm. Okay? But this is less than equal to eta, this is less than equal to epsilon. No, I mean, so okay, let me define. So what is the definition of a dual norm? This is a definition. I am saying that from these things, it follows that f phi is less than equal to norm of f into norm of phi. Because you just take here, then f by norm f becomes a norm 1 function. So there is no Cauchy Schwarz, it is just the definition of a dual norm. That's all. Okay? So therefore, fine. So therefore, this is less than equal to norm of phi star into norm of v minus 1. So now total how much I have got? I have got here 1 minus delta. I have got here eta epsilon. Now I can choose my eta epsilon so that this is less than delta. My epsilon to be, let's say, delta by, if I choose my epsilon to be delta by 2 eta. Yeah? Then this thing will be less than equal to 1 minus delta by 2. But on the other hand, this guy is greater than 1. And hence I obtained a contradiction. Because of that is how we have got a function. Right? So that gives us so therefore so far I have not even, if this phi would have been a positive function, I have not used the fact that this is an algebra norm. Yeah, 5 minutes. Okay, let me now in this next 5 minutes try to prove this result, and without assuming that phi is non-negative. Will I be able to? Or should I stop here? It's not long. Sorry? This condition is equivalent to saying that the norm of dual of phi is less than or equal to eta. In this corollary, because what is this condition meaning? F2 of phi is less than or equal to 1 for all F2 with norm F2 less than or equal to eta. Or maybe eta inverse, sorry. You are right. Yeah, you are right. It is eta inverse and not eta. But anyway, so okay, I have to choose the delta by 2 eta. Okay, I'll prove, I think, tomorrow. Otherwise, I will end up taking more time. Let me stop here.